for it is more of like to know the structure that will be produced, and because of the production of structure, what type of bonding it may have. So Lewis structure is quite important and very helpful for us to understand or to perceive the structure of an molecule. And Lewis structure will be based on their octet rule. All right. So since we are talking about the octet rule, it should be bound by their valence electron not more than 8. There is always exception. We will be talking about it. But the good thing is, without exception, not without exception actually, there are the d orbitals. Those who have d orbitals, they do not follow this Lewis structure or octet rule. So that is why it is very hard for those type of elements to predict the Lewis structure for them. So what should we do for them? Well, for those who has d orbitals, we go for molecular orbital theory. And you will be learning by yourself, but I'm here to help anything for your assignment 1 that has been already given to you. But if you have any question, any problem, any understanding, then let me know so that we can discuss. In fact, I will ask you all to come and discuss your progress from next week on. And another thing is for your test. Okay, let me remind you again. The test is coming on next week, right? Tuesday. Tuesday. From the time and date is given on the announcement, this week announcement. I re-edited it. I edited later on, and then you can find from there the link. You will have to do the test, like a descriptive question. So you have to do it by your hand and then upload it to the link on Canvas. And also there will be a link for you to take individually your quiz. So there'll be quiz and descriptive or essay type questions. Quiz you will do straight away, just click on the link, just like the quiz that you have taken. But for the descriptive question, you have to do it, download it, or you see on screen your question and then solve the question and then upload it again to the same link, the link that will be given there. So that is just a reminder that the test is coming up. And it is time bound, so there will be within some time frame you have to finish the descriptive question. For quiz, there is time bound as well, but there is a wide range, or what do you call it? The validity of the quiz is quite longer. Maybe it will be for 3-4 hours. So once the students start, within these 3-4 hours, you have to start the quiz. After that, the quiz, the link will be vanished. So if you start within this given time period, you have to finish that quiz within like 30 minutes, 20 minutes. I'm not sure yet. I haven't set the quiz. So you have to finish within that time period. Although the link is valid for 2-3 hours, but once you start within these 2-3 hours, the link will expire 20 minutes or 25 minutes after you have started the quiz. So be careful on that as well. Okay, so now come back to that Lewis structure and octet rule. So period 2 elements and hold on. Let me take the pen. So period 2 elements and carbon, nitrogen, oxygen, and fluorine, but it can go beyond that, like the halogens we can do, and also can do for this sodium, potassium as well. But in between this, there are from within this period 2 elements, period 1 and 2 elements, there will be an exception that they do not follow the octet rule, or they do not produce the octets. From the elements up onward, from the they will not strictly follow the octet rule. They can have more than 8 electrons, right? So since they have more than d orbitals, they can have more than 80 electrons. And interesting thing is, it is still very fluid concept, still fluid concept. Many scientists are arguing for this case or that case. Some are saying that why it will go expansion of octet means what, because 3p and 3d, the energy difference is not that high. So when it is telling d, p can go to d, d can come to p, why we need to consider the expansion of the octet. So that is the big debate still in the scientific community for scientists in this field. But for us, for the learning, so for us, it will be good enough to know that from period 2 onwards, it is very hard to predict the Lewis structure because of the expansion of octet. Okay, so how do we draw the Lewis structure? For the first one, right? This is aluminium triiodide. Oh, okay, aluminium AlI3. So probably we can put I in this form so that it is much easier. Aluminium I3 triiodide. In this case, as we know that from the periodic table, right? From the periodic table, let me go to the periodic table, show you just in a glimpse that, where is it? Hold on. Here, but from the periodic table, if we look at there, let me share the screen so it will be better. So if we look at there, you see that aluminium is here, right? Is 3, group 3, and then it has 13 electrons. So unlucky or whatever, just okay, it's a joke. So silicon, aluminium is 13 electrons. So if we go and see the electron, what do you call it? Configuration is 2s2, 2p6, 3s2, and 3p1. There is one electron at the end, at the other side. And p orbital. So since how many electrons can p orbital have? P orbital have a maximum of 6 electron, right? So 6 electron p orbital have, and then with the 6 electron, how many bonding it can make? Each bond takes 2 electrons. So 3 bond it can make. But it is an exception. Another exception for aluminium per se is that aluminium, since it has 3p, it also has 3d orbital as well along with it. So it can go beyond that sometimes. Okay, so this is another, first one, right? And then let's go back to our lecture slide. So for exception for aluminium triiodide, what we will do is we will to draw the Lewis structure, the first thing we will do is to count on the valence electron for all the elements involved in that element, in that molecule. Molecule means the aluminium triiodide is the whole molecule, right? Aluminium triiodide, the whole molecule. So there is aluminium 1 and iodine. 2 elements are there, and each element will have electrons, the valence electron outer side of it. So the valence electron for aluminium is 3. We have seen already 3s2 and 3p1. So that is the outer shell, 3s2 and 3p1. So that is the valence electron, 3 valence electron. And for iodine, if we go back and to the periodic table, we will see that iodine has 7 electrons at the valence shell because this is a halogen. So they just need to 1 more to make to the what is that? To go to that inert gas. So it has 7 electrons, and then there are 3 of them. there are 3 of them, so multiplied by 3. So altogether they will have 24 electrons. Now we should draw aluminum triiodide in a Lewis structure in a way that it make up all these 24 electrons all around it. It should be able to make up all 24 electrons around it. There should be no less, no more. Okay, so now we draw it, aluminium being the less electronegative among these 2 different type of elements. Aluminium is at the center. All right, aluminium is at the center, and then iodine is surrounded to it, to the aluminium. So now we, since there will be bonding, we just put 1-1-1 bond, and then we fill up the octet for iodine, because iodine is more electronegative, so it will draw electron towards it, right? So iodine is filled up. Each of them has 8 electrons, right? So here is 2. 2 is here. I'm drawing too much, is it? So iodine will have 2 electrons in it. Each of them, I mean, has 8 electrons, but 6 electrons are paired. Iodine has 6 electrons paired, and then 1 electron, I mean, 2 electrons are shared with aluminium, which is 2 electrons here, right? So each iodine has 2 to 4 plus 2 is 6 plus 2 from this bonding, which is shared with electron, but still count. So this is 8 electrons for 1 iodine. The same goes for, it's identical, this iodine, and no difference between them. So this is 8, that is 8, and this is 8 as well. So 8, 8, 8. 24 electrons altogether it has. And now we see that iodines are filled up with octet, or I mean octet are filled up, so they are very much similar to that argon structure, that is an inert gas. And aluminium is also filled up because 6 electron it can have, and it is having 6 electron altogether. So this is Lewis structure for aluminium triiodide, and this is an exception for it. Incomplete octet. There are 2 other elements that will have incomplete octet. We will find it out, and there are we'll talk about it later. So the Lewis structure for phosphorus pentafluoride, it will be another interesting thing. Phosphorus pentafluoride. Fluorine being a very electronegative, so it needs just 1 electron to fill up its octet, and it will take the electron from phosphorus and make a bonding. So again, there's the first rule is total number of electrons. Total number of electrons we will be searching for. So phosphorus has 5 electrons, group 5 element. So it has 5 electrons, right? So at the outer shell, and then phosphorus has 7, but there are 5 phosphorus element in there, atoms. Sorry, 5 phosphorus atoms are there. So altogether is 40 electrons. And now I have to make a structure that satisfies these 40 electrons all around it, and it can house it without having to excessively, I mean, violating the rule of one atoms, its own rule. So how do we make it? Phosphorus being less electronegative at the center, and fluorine are all around it. First. Second thing is fluorine cannot have more than 8 electrons. It will not take more than 8 electrons. It can make only 1 bond, and it is impossible for fluorine to make 2 bonds, and it will not be stable. So each fluorine are having 8 electrons because it's negative, so it will be 8 electrons. It will fill up its octet. So 8 electrons it has altogether, all of them, and there are 5 atoms of fluorine all around. So 5 times 8 is 40. So it satisfies the number of electrons all around it. But the question is, phosphorus is having 1, 2. Is it software problem or is it Microsoft Office problem? My computer problem. So this is number 2. This is number 3. This is 4 and this is 5. So 5. How many electrons? What is the number of total electrons it has all around it for phosphorus? Anybody? How many electrons does phosphorus have all around it or outer shell? Total phosphorus, I mean number of electrons phosphorus has. Any idea? Tell me. Can you tell? Just give me the number. Five times 8, yeah? Is it? Don't be deceived what I'm saying. You just tell me what you believe or what you understand. Not believe, what you understand. Phosphorus is having 10 electrons all around it. And this is a bit doubt. I mean, oftentimes we can have doubt on this. How come it can have 10 electrons? Maximum can be 8. No, phosphorus is again an exception that it can goes beyond this octet rule because it has d orbital. It is you know, it has the d orbital. Is after aluminium is coming in the 15 group, so that it can have more than 8 electrons in it. Okay, so expansion of octet, that's called expansion of octet. The expansion of octet is quite interesting and it's quite sometimes not difficult, but takes some attention for us to complete or to understand how this will happen. Now, the nitrogen dioxide. Once again, I'm telling that all the molecules of nitrogen, you should be taken. I mean, it should be taken care of. Nitrogen oxide, because nitrogen is a bit, you know, problematic for us. There will be single electron, unpaired electron, more than, I mean, positive charge, sometimes negative charge. So this is the thing. So nitrogen dioxide, once again, we will do that total number of electrons. We'll try to figure out what is the total number of electrons. Nitrogen has 5 electrons, valence, outer shell, electron 5, and oxygen has 6 electrons, outer shell. And there are 2 atoms of oxygen here. So all together 17 electrons. Now there is a problem. 17 electrons is uneven number, right? It's the odd number. It's odd number, but I have to make it because there is a nitrogen dioxide gas and it is present and it is stable to some extent. It's a stable nitrogen dioxide. So what we'll do is, which one is more electronegative in, among them? Which is more electronegative among them? Of course, oxygen. So oxygen cannot be at the center. Nitrogen should be at the center. Okay, nitrogen is at the center. And then, of course, we put the oxygen all around. 2 oxygen we put all around, and then start to fill up the. Better I should do in this way. Hold on. I draw it first. So this is nitrogen, and I'm putting oxygen on both sides of it. Okay, although there will be a not a straight line, it will be a cone, but anyway, so this is nitrogen and oxygen. So now what I'll do is I will make one bond, because at least they should have a bond, at least one bond they should have, right? And then the rest of the bond electron I will try to fill up with the oxygen. So 2, and then another 2 is here, and another 2 is here, right? So 2, 4, 6, and then including this bond 2 electrons, 8 for oxygen, and then here is 2, 4, and then 6. So 2, 4, 6, 8 all together. So 8 plus 8, 16, and then another 1 electron is left. So 8 plus 8, 16, 1 electron is left behind. So where should I put it? Put it on oxygen, is it? Put it on oxygen. If I put it on there, let's say this oxygen and this oxygen 1 and oxygen 2 are same thing. Same thing. There is no difference. I'm putting this electron here, means I can put it on this oxygen as well. Same thing will happen. So I'm putting on oxygen 1 electron. So I'm putting it on oxygen. And now what is happening for this oxygen? This oxygen go beyond 8 electrons. Now it is again going to this sodium, and it will not do that because it is by 8, it is the maximum stable. It will not leave this comfort zone because it's so stable and so what is that? Okay, stable. Oxygen is so stable in these 8 electrons when it is having an outer shell that it will not take any more electrons. It's almost impossible to put 1 more electron to oxygen. Okay, so what we'll do is, on the contrary, there nitrogen has only 4 electrons, 2 and 2, 4, and then nothing else. So we can just put 1 more. Try to make it a bit more so that it has a little bit more. It doesn't feel deprived. So that 1 more electron, but it does not satisfy that nitrogen. It has 5. It also has 5. So what is the purpose for it to make a bonding, right? It has 5. It had 5, and now it is having 5 as well. So what it will do is the oxygen, it will push or negotiate or whatever you call it to the oxygen to give these 2 more electron towards it. So when I'm saying that, okay, from this oxygen number 2 is same thing for oxygen number 1. It can get from here too, and it will have it when we go resonance structure. We'll see. So it will force this one to get 2 more electrons. Okay. It will take 2 more electrons from this oxygen, and then by force or by because of its electron deficiency, it will take 2 more electron and ask it, oxygen, how does oxygen give? It does not just give 1, 2 electron to nitrogen like this. If it gives like this, so what will happen? What will happen is that oxygen is becoming deprived of electrons. If it just donate 2 electrons to nitrogen, oxygen is now having 6 electrons. That is the same thing again, right? So oxygen will say, okay, why don't we just share both of them together? So just hold on here. So what we'll do, oxygen is just taking 2 electrons, donating these 2 electrons to nitrogen, and then there is a double bond nitrogen is making. All right, double bond nitrogen is making, and this double bond, now I move it here, delete it from here. So this double bond, when it is there, oxygen is still having 8 electrons. This oxygen is still having 8 electrons, and now from 5 electrons, nitrogen is having 7 electrons. 3 times 2, 6 plus 1, 7. So it is much closer to 8. It's much better than 5, having 5, right? So this is the thing that nitrogen will have. And then hold on, 16 electrons, right? So 2, 4, 6, 8, 10, 12, 14, 16, 17. Yeah. So this is how it will go on. And then this is the different thing. And this oxygen has, there is a mistake here, it will be one oxygen, yeah, one electron here. So this oxygen odd electrons, this oxygen is having one electron, sorry, for the glitch. Okay, so in this case, another possibility is that oxygen is giving nitrogen is taking two electrons by sharing with oxygen, right? Sharing with oxygen, and then it has 2 and 2, 4, plus this 2 means 2, 2, 4, 8. And then this oxygen is having 6 electrons. This oxygen is having 6 electrons all around. Why it is happening? Why it is happening? Sorry. So this oxygen is having 6 electrons all around it. This, so 1 electron. So another possibility that this nitrogen will fill up its octet unless, this is one scenario, number 1, or number A scenario. Number B scenario is that nitrogen is taking 1 more electron from oxygen and getting it to itself. So nitrogen is becoming 2 electrons, and after being omitting from here, oxygen is having 1 electron to it. So there are 2 scenarios actually. In this case, which one will be more stable? Which one will be more stable? Which one will be the actual structure? Whether it's structure A or structure B, oxygen will have 1 electron on it, or oxygen will have 2 electrons on it. Which one is more preferable? One question I'm leaving here. I will come back to this question later on. So how do we know that which one will be more plausible, more logical, or more stable for this nitrogen dioxide structure? We have to know some other parameter. That parameter is called the formal charge. Okay, the formal charge. After they are separate, they have constructed a structure, Lewis structure, they will form some kind of charge among them. There will be some kind of charge among them. Of course, if there is no charge, that is much better. But unfortunately, most of the time there will be some charges, this type of molecule, when there is disparity of electrons. So I will come to that formal charge in a bit. Now, exception of octet, barium and beryllium, right? They are group 2 element, so they will form, they do not have this octet will be not filled. There is the incomplete octet, just like aluminium. And also for hydrogen only needs 2 electrons. No, it doesn't need 8 electrons, right? Expansion of octet, phosphorus, then sulfur, then xenon. All right, xenon. So all of them, and some other, now I cannot recall, but as we go to that examples, we can see. So xenon, all of them will have expansion of octet. They can have more than 8, more than 20, 15, 16 electrons they can house around it, just because they have these d orbitals around it. Odd electron molecules. So nitrogen, just now we have seen that nitric oxide, nitrogen dioxide, then chlorine dioxide, these all can have odd electrons, and this takes a little bit of attention and practice. If you just listen it here and you think that, okay, you can do it, you have understood, that will be a mistake. at least 2-3 times you do it on paper with your pen. Take a pen and try to do it on a paper. You will see that some of the details that you did not listen or you did not take note is coming to your understanding. So at least try 2-3 times at home before there is a test. Yeah. And draw the Lewis structure for the following compounds or ions. This is for you to try at home, and not at home actually. It is supposed to be done now, and I am going to ask you to do some of them now. We are in okay. We are in 37, so we have another 10-12 slides to go. Okay, I do it first. Then maybe if I have time, then I'll go for that practice. Example 9. It says that draw a Lewis structure for the sulfate ion. It is much interesting again. Sulfate ion. Where does this sulfate come from? Anybody? Where does this sulfate come from? How we can get this sulfate ion? From which type of compound or which type of reaction we can get this sulfate? Anyone wants to shout? From which type of reaction, which type of compounds we can get sulfate? Sulfur dioxide, I mean sulfuric acid, right? Sodium bisulfate, potassium bisulfate. Yes, great. Audrey, thank you. The sulfuric acid, and then from sulfuric acid, really we get the sulfate. I'm not confusing you, but there are many details that we should know, or as a student of chemistry, we should know. From sulfuric acid, there is a possibility that we can get the sulfate ion, but yeah. Any other option? I see Ainin is typing. Let the answer come out. Don't give any spoiler alert. It's time consuming to type. Ainin, you can just unmute yourself and talk. We already have talked. We already have talked, so we know. Ainin, I saw you typing. Where did you go? All right, for sulfuric acid, we can get bisulfate, HSO4 -1. Okay, HSO4 -1 is bisulfate ion we can get, but to get sulfate ion, it's too difficult because it takes much energy to break away from hydrogen. But if I have sodium sulfate or potassium sulfate, it's much easier because that is a salt. That is a salt, and salts are polar, and they are what do you call it? They are soluble in water, and they are readily what is that called? The term called? They can readily dissolve in water and produce this different type of ions. So from the salt, it is much easier to get the sulfate. But anyway, they cannot stay as it is, right? They cannot, the sulfate and phosphate and whatever, they cannot stay as by themselves. They have to be in association with someone. But in the solution, the sulfate. But if there is a sulfate ion, how do they look like? How does it look like? So to know this one, to get at least some rough idea of how sulfate may look like, we have to understand, or we have to draw a Lewis structure for them. So what's the first thing do we do for for drawing a Lewis structure of sulfate. We will first count on the valence electron of sulfur and oxygen. So sulfur will have 6 electrons because sulfur and oxygen is the same group. So sulfur and oxygen we will have count on, and then the oxygen has 6 as well, the valence electron, and there are 4 oxygen atoms all around it. So this is, but the problem is there are 2 negative charge. 2 negative charge. That means 2 excess electron is there. 2 negative charge means 2 excess electron is associated in this ion. 2 more electrons it has. So the 2 electrons should be counted as well, right? So all together is 32 electrons. Now 32 electrons is so easy. We just make it 888. I mean 1 bond each to oxygen, and then fill up the octet. 8. That's good. And then all together. So this is 8.
Sorry, sir.
Yeah.
Are you showing something, another slide? Because we're still on the exercise draw Lewis structures slide. It's like the slide is stuck there.
Oh, okay. Let me check. So can you see now?
Yes.
Okay, okay. Thank you for the notification. Okay, so sulfate. Yeah, I was showing the sulfate ion, and now was telling that sulfate has altogether 6 electrons for oxygen, 6 for sulfur as well, but there are 4 electrons all around it, right? 4 electrons, 4 atoms of oxygen are around it, so that we will have altogether is 30 electrons. 6 for each for 4 oxygen, and then another 6 for sulfur, plus 2. The negative charge has 2 electrons. That means 2 negative charge means 2 electrons, right? 2 negative charge, that means 2 excess of electron it has, and that should be counted. That should be added up. That should be added up to this total number of electrons. So altogether is 32 electrons. It has 32 electrons, and looking at it, 32 electrons is so easy for us to draw, because we can just make 1 bond to oxygen each from sulfur, and then fill up the octet of all around the oxygen. So each oxygen will have 8 electrons, right? 8 electrons, and then 4 times 8 is 32. That's so easy. But there is another possibility, that the sulfur can take these electrons, can draw this electron towards it. All right, draw this electron towards it, and then make the double bond, and 2 electrons, 2 oxygen ion become negative, and that one, because there is 2 negative ion, we have to to show that there are 2 negative ions. It is having 2 negative ions on it as well. So there is another possibility. So which one will be possible, or will be actual thing? Because just from Lewis structure, it is not serving our purpose to understand what type of structure or what the structure looks like. All right, so this is the formal charge is coming into play for this thing. So if we want to know which one is more likely, this one, A or B, A or B, which one is more likely, more possible, or actual thing? Actually, we go for the formal charges. Formal charge is the total number of valence electron in the free atom. Total number of valence electron for the free atom minus total number of non-bonding electron still available after they have formed the bond. Total number of free electrons, non-bonding electrons, not free, sorry, non-bonding electrons, number of non-bonding is still, after they have made the bonding, is still available, minus the number of bonds it has made, or half of the total bonding electrons it has. So if we do in this equation, we will find the formal charge that will be on each of the elements. So for sulfur trioxide, tetroxide, or sulfate ion, so this one, sorry, how it becomes, so, sorry, this is not the correct photo. This one will be the B structure. So two of them has two negative, double bond of oxygen and fill up the octet, and two of them has single bond oxygen, which is carrying the negative charge. All right, so this is another option. So which one is more stable or more plausible? Let's calculate the formal charge on sulfur first for structure A. So this is structure A and this is structure B. Formal charge for structure A is for sulfur, we see that it is 6 electron. It has, because valence electron for sulfur has 6 electrons, right? We started with. Now, after it has bonded with 4 oxygen, we see that there is no more electrons available on the sulfur. No more electrons. It does not show any, and it is the octet is filled up as well. So there is 0 electrons, no more electrons here. Minus how many bonds it has made? 4 bonds, or 4 bonds involve total 8 electrons. So half of 8, that is 4, of course. So that is the positive 2 charge on sulfur. So put positive 2 charge on sulfur, right? And then for oxygen, because all the oxygens are same, one single bond to each of the oxygen, it is identical. Whatever will be for this oxygen will be the same for the other oxygen. So just calculate what is the formal charge on this oxygen so that we know what is the formal charge for other oxygen. Now we see that 6 oxygen also has 6 valence electron, but it's still, after it has bonded, still there are 6 electrons in it, right? So 2, 4, and then 6. So after it has bonded with sulfur, still it has 6 electrons in it. And then half of the total bonding, that means 1 bond only, so 1. So that will be -1 charge. So each of them has -1 charge. -1 charge, -1 charge, so -1 and +2, both of them cancelled out, and then -1 and -1 will be left over or will stay. So that satisfies. So it is also looks correct, because the formal charge, total formal charge is also correct, and that is the charge we found. But for this case, for the B, we see that for sulfur, the total charge is 0. So the sulfur total charge will be 0. And for oxygen is -1 for those oxygen that is one single bonded oxygen. So single bonded oxygen, it has -1 charge each. And this oxygen, which is double bonded, this is 0. Formal charge is 0. So it is not carrying any charge. It is very stable, and they don't want to carry any charge. Sulfur is also very stable. It doesn't carry any charge. It doesn't have any headache. But these 2 oxygen, it is having negative charge each. So now, which one will be more stable? There is a guideline for which one will be more stable. So for neutral molecule, having no formal charge is preferable. Neutral molecule. Neutral molecule means those who are not very much electronegative, those who does not usually form charges. So this type of neutral molecule, they will have formal charge. If there are formal 0 charge, that is much more favorable and preferable as well. Smaller formal charge are preferable to longer formal charge. If in this case, there were 2 positive charge right here for sulfur, but here it was +1. It would be more possible, because positive 1 is less than positive 2. So less positive, charges, formula, whatever, less positive or negative, whatever charge, less is better. Negative formal charge should be on the more electronegative atoms. Since oxygen is electronegative more than sulfur, if you put the formal charge negative formal charge on sulfur and oxygen positive, it will be very unstable. It is very unstable. Oxygen doesn't want to agree with that. Okay, one thing. And similar formal charge on adjacent atoms are not desirable. That means here it is. So if two formal charges, let's say that we are choosing this because it is here, and we want to put two double bond here to this oxygen and one double bond to this oxygen, and each of them are carrying -1 charge, right? It would be wrong, because these two negative charge by this very near the neighbors, they will start having a tension, two negative charge. So they do not want to do that. They will be negative charge but far apart from one, the maximum possible, the distance, so that there will be less interaction between them, or less hindrance or less friction between them, so that will be more stable. And that is why we cannot put this formal charge together adjacent atoms. Okay, we cannot put this formal charge to adjacent atoms. It should be far apart. And that is why the structure 2 or B is much more possible or favorable. And to get to this structure 2 or B, we have to have this expansion of octet for sulfur. Sulfur has already 2, 4, 6, 8, 10, 12 electron in it at the outer shell. 12 electrons, but still it is stable than having 8 electrons. Okay. Another thing is, although we are saying that is much stable, much possible, favorable, and these two oxygen atoms. Let's say this is oxygen atom A and oxygen atom B. A and these two A's are same, these two B's are same. So that's why I'm just denoting A and B in there. So does it mean that only B will have double bond, very stable, and A will not have the double bond? Only be stable? Not like that, because all oxygen are same atoms. They are same atom. So what will have? They will have some kind of resonance. This double bond will shift from one to another one, right? So that is called the resonance. And how do we know that there is a resonance? From the X-ray diffraction, for a sulfur oxygen single bond, it was found that it is 157 picometer. Very small, but 157 picometer, the length. For SO double bond, it is 142 picometer. So in this case, if we would do this in the analysis in the X-ray diffraction, we will say that this is 142 and this is 157, but it is not like that. Interesting thing is, all together we find that all the bond, this bond, this bond, this bond, this bond, doesn't matter double or single, it has 149 picometer, an average, all of them. Interesting, right? So what is happening? Because of the resonance, this double bond is shifting to here, and the next moment this double bond is shifting to here, right? And then it becomes single, it becomes double, and then this double again coming to here, and this double is going to there. So in this way, it is not clockwise, it is randomly going, changing the order, the bond order, 2 to 1, then 2, 2 to 1, and 2, and it is happening very fast, like how to say that, unbelievably fast it is happening. Right, so that is why we get 149 picometer, the sulfur and oxygen distance, and that is called the resonance. This is the resonance structure of sulfur tetrox sulfate ion, right? Sulfur tetroxide. Right? ion. So this is the resonance happening, and the negative ion is also changing accordingly. When it is becoming positive charge, it is getting negative, and it is become neutral, and so on. It's always happening, and it is continuing. That is called the resonance structure. So it cannot be represented accurately because all the same time it is single bond and double bond, and that is why we call it resonance structure. And resonance structures are much more stable. Right, so this is ozone structure. This is ozone, and we see that ozone. There is no other better way to represent ozone structure than this. But then, if we do this oxygen, ozone is stable, right? Ozone, the ozone layer to some extent is very important for us, for our living, and also you get oxygen from there. And then if it's too much, then it's problematic. Too less, also problematic. But anyway, so ozone is like, it is, but it's stable. Although this oxygen is having negative and this oxygen is positive, oxygen is negative is better than oxygen having positive, because positive it cannot stand being positive, is electronegative, so it does not want to lose electron. Having electron on it is better than losing electron for oxygen or for electronegative elements. So what will happen is it will continuously having the resonance at the same time, single bond and double bond, so that the charges are moving all around on the molecule. And that is why it is having the resonance. Formaldehyde, a liquid with a disagreeable odor, traditionally have been used to preserve laboratory specimen, draw the most likely structure for it. So formaldehyde, there are 4 possible structure it can have. Which one is more plausible? Again, we have to find out the formal charges on each of the structure, right? Each of the structures. So one is this, another one is this, one is this, and another one is this. So in broad way, we can divide into 2, because this is the 2 things, similar thing. And if we take these 2 and find out what is the resonance structure, formal charges on it, we will see that where is the most less charges. This structure has the less formal charges on it, and that is how it will be very stable. Dinitrogen oxide, the atomic array is NNO, indicate the formal charge and rank. So NNO, dinitrogen oxide, okay, so it can have double bond, it can have triple bond, and oxygen also can have triple bond. These 3 possible way it can form we can draw the structure, but which one is stable and which one is the actual structure? And if we draw all 3, the number of valence electron will be satisfied. If we count on the valence electron, the total valence electron is same for A, B, and C. But not, 2 of them is not possible. Which one is not possible? If we look for these formal charges, NNO, where's NNO? Okay, so formal charges, N2O structure possible is B. We will see, you will count on the valence electron, we'll see that the formal charge is B is most plausible, most favorable, not the one. Oh yeah, formal charges are given here. So nitrogen, it has 2 negative ion on nitrogen, and then this nitrogen has only 1 positive ion on it, so that it is not stable on it. Okay, so for this case, among this B, A, B, and C, B has the least amount of charges on it. So that is why it is much more plausible, much more stable in this way. Okay, so this is exercise 2. You will be doing more and then try more about it. And we are time out. From among these structures, so do some exercise at home so that we can have fun during the Menti question next time. Okay, so all the best. This is it. Do you have any question, anybody? Anyone has any question?
No, sir.
All right. Anyone else has a question? Okay, good, good. Thank you. So all the best. Have a nice evening and have a good class from who are having class now. All the best. See you next Monday. Take care. Bye-bye.